Hello students, welcome back. Here's an important topic, linear regression. One of the most important topics for entire first half of the course. Okay, here we go. Let's begin with some motivation examples. Okay, we have some scatter plot and the line of best fit, the regression line, but it's a bit difficult here because the dots are a bit too tightly packed along the line. So instead of Dallas and New York, let's go to some other case. Dallas and Honolulu. Okay, this looks better because the diagram is a little bit fatter, so I can see the error a little bit clearer here. Okay, what we are looking for is the equation of the regression line. Once we find the regression line, this equation of the line, then we can do the regression prediction. So what is the regression prediction? So the regression prediction the regression prediction is a process to find the best value of y for given x value. What do you mean by best value? The value that will minimize all possible errors. Look at the picture. For example, if x value is given as, let's see, about 85, and the best prediction is the y-coordinate right on the line. And we may end up with some higher number or lower number as in case, but this goes pretty much in the middle, so that's the best point prediction. But then again, nothing is accurate in statistics. Here's a real value, again for the given same x value. So the difference, the prediction error, is the vertical distance. The regression prediction errors are depicted in the above graph. The regression prediction errors are depicted as the vertical line segments. So prediction is the y-coordinate on the line, and the actual observed value is a little bit down below. So the distance, the vertical distance, is the prediction error. It should not be tilted, not be horizontal, it should be vertical because x value is given and x is fixed. X is fixed as 94 or something like that. And here is predicted value and then here's observed value. X is fixed as 85 and this is actual value, this is predicted value. That's the difference. In some cases the difference is really small, so very small error, and some medium-sized error, some large errors. We can have all kind of things there. Now, what's the nice thing about regression prediction? The regression line minimizes sum of the squares of the errors. You see, not the sum of the errors. If you just add up all the errors, then pluses and minuses will cancel each other out, then you're going to get 0 in the end. That's not what you want. So how do you measure the dispersion? Make the squares to make everything positive and then add up. Now, the regression line minimizes that sum of the squares of the errors. If you select another line, and then take the sum of squares, it's going to be bigger than that of the regression line. So the regression line is the best prediction here. So the regression line gives us the best point prediction. And for this reason, So the regression line is often called the least square line because it minimizes the sum of the squares. The sum of the square errors. So it is called the least square line. It has many names: least square line, the line of best fit, the trend line, but my favorite is regression line. Our aim is to find out the equation of the regression line. Once we find it, plug in x value, calculate, and that's the y-coordinate value that we are predicting. It's not always accurate, but it'll minimize the error. Now, how do we actually find out the equation of the regression line? That's a big question. But then again, we have these two really nice formulae. Oops. Okay. Make it even bigger. It is based upon the slope point equation of the line. The regression line runs through the average point, x bar comma y bar. Here are some visualizations. Let's see. Okay, New York and San Francisco. Here's a mean x bar y bar, and the line is running through that. Dallas and Honolulu. Well, here's the average point, x bar y bar, and the line is running through that, etc. So you can use the slope point equation. This is a slope and running through x bar comma y bar, and here it is. X bar, y bar, Sx, Sy, and R are all available in problem somewhere, and X is also given. Put everything in there, run your calculation, and that is your regression prediction. Now, this is the textbook's method. Instead of using slope point equation, our textbook author uses slope intercept equation. Find the slope, and then use that to find out the y-intercept, and then plug everything back into the slope intercept equation and plug in x and do your computation. You're going to get the same value as before, but this is a three-step process. And each of that three-step process is just as difficult as this single step. So this method is basically 3 times as difficult as this method. I don't like it. I'll cover it, yes, because it appears in our textbook author does it, and even more importantly, my math lab is forcing you to do it this way. I hate it, but I have to cover it, so I'll do it in a separate video. Here, or in the majority of the class, I'm going to do it this way. I'm going to take a single step method. Okay. Here's a problem. Here's a score table of a certain class. Ooh, we have too much information. But actually, what it really counts is just these. You see the correlation between exam 1 and exam 2 is given as this. R value. And we want exam 1 and exam 2. So exam 1, first column, exam 2, second column. So this is coming from exam 1. And that's for exam 2. Okay, midterm exam is blue, final exam is red. See the color coding? And midterm exam score is 93. So we have to find out the final exam score, or the best point prediction of it. Okay, here's the formula. Let's use that. And then x value here is going to be 93. And then this is going to be regression prediction. So let's use y hat. And that's going to be the final exam score. Now x is known and y is unknown. Mean of x, blue. Mean of y, red. Standard deviation of x, blue. Standard deviation of y, red. Final. And then the correlation coefficient. Color coding helps actually. And do your computation. So R value, it goes there. Sx, what is the standard deviation of x in this case? For exam 1, because exam 1 is x, it's right here. And the mean of x is right there. Do you see the color coding there? So x is exam 1, y is exam 2. Because we know exam 1 score, 93, and we want to find out the exam 2 score, that's unknown. So that's the method you're going to be using, and here are the numbers to plug in, and also R value. Make sense? Okay, you can go ahead, stop the playback and go ahead on your own. Well, here it is. Exam 1 score is your x, and exam 2 score is your y. And based upon the slope point equation of the line, we get this kind of computation. Okay, scroll a little bit so that I have the same viewing window. That's midterm, that's average for midterm. That's the mean for final. And this is a standard deviation for midterm. This one is a standard deviation for final. And this is a correlation coefficient. Run your calculation and you're going to get about 86. So the best point prediction is 86. Now, do we have enough time for second problem? Okay, let's go ahead and do that. Let's see, same structure. And use a method of linear regression and the best point prediction of the midterm exam score. So this time we don't know midterm. And the final exam score is 86. So what's the difference this time? X is 86. X is known, so this time X is final. Previously, X was midterm, but this time it's different. X is final. So midterm is Y, and final is X. So X bar is actually final. Y bar is the midterm. See this flipping? So this time Y is midterm, X is final. They are switched. Do you see the difference in color coding? Sorry about that. So X is exam 2 score. So Y is unknown, and that's the midterm exam score. And you can calculate it using this one-step process. Final score is known, so X is final, so X bar is for final, Y bar is for midterm. And down below for final, up here for midterm, and of course this is neutral. And that's how you do your computation. Remember, X and Y are switched compared with the previous problem, because this time X is known, so final is known, and Y is unknown. That's why they are reversed.